Okay, we are currently 15 minutes late. I will have to speak very fast. I apologize. In any case, thank you so much for coming. Thank you so much for waiting. I understand it is really frustrating for this to happen. We had some issues, but I think now we can begin. In any case, my name is Hillel. This is a talk about how everything about distributed systems is terrible, because as we all know, they are terrible. More specifically, we are talking about TLA+, how we can actually make them less terrible. We're going to cover why they are tricky and why a lot of our tools don't quite work to deal with them, and how we can use better tools such as formal specification to deal with them better. Now, this is one of the most common quotes about what makes a distributed system a distributed system. And if you haven't seen this, Leslie Lamport is probably one of the biggest names in this field. He's done a lot of work on both defining it and fixing it. But his joke here is funny, but doesn't really cover what makes these hard. So I want to give a different definition, one that more closely covers what we're actually talking about. A distributed system is one that has multiple agents, independent actors who are not synchronized. They have global properties, that is something that all of them independently contribute to that we want. For example, with a database, multiple nodes can have the global property of consistent data. We also have localized information. That means there's something about these agents that we cannot extract without effort. As a simple example about this, consider a server. It's either online or offline. But to know whether it's online, you have to find out. You have to use a heartbeat, you have to send a query, something. You cannot just assume, and you cannot just find that out. Figuring out that local information is part of the design itself. And then finally, agents can go down. What we mean by that is that if some of the agents stop working, we still have a working system. Now, who here, raise your hand if you've worked with a distributed system before of any type? Cool, that's a lot of you. I'm sure you've all had issues with it. Raise your hand if it's been terrible to you in some way. I don't think a single hand went down that time. They're kind of problems, but I think when we talk about why they're problems, we're usually talking at the surface level. Things like Kubernetes is awful, or things keep crashing, or duplicate messages. These don't really talk about why these are fundamentally a problem. And to sort of explore this a bit, I want to give you two examples of systems, one distributed, one not. And I want you to raise your hand on each one if you think it is in some way, quote unquote, hard. First one, we have, clicker isn't working. First one, we have two servers, two clients, and a single server. The clients are non-transactionally talking to the server and updating its information. Raise your hand if you think this is quote unquote hard in a distributed system way. Some of you. Okay. Same thing, but now we have threads. So two threads sharing memory. Is this hard in the same way? I'm seeing a lot fewer hands up, which is reasonable because this is not a distributed system. But the interesting thing about this is that if you look at the history of us trying to formalize these fields, we often end with the same people working on both. We're talking Lamport, we're talking Nancy Lynch, we're talking Edgar Dijkstra. And it turns out that a lot of the ways they used to understand each system were very similar. We can use the same ideas for both low-level threading and high-level architecture to figure out what makes them easy or hard. That's what I want to talk about right now, what we can do to understand these systems. We have this formalism we call the state space. To show what this likes, let's take a simple example to start. We have X globally starting at 1. I don't care what it means to be global here. I don't care what the agents are. They can be threads, they can be processes, they can be servers, they can be clusters of servers. One of them is going to increment X by 1. The other will double it. I want you all to take a second and think, how many values can X end here, assuming that X starts at 1? Everybody take a moment to think about that while I drink some water. OK. There can be two. X can either double then increment or increment then double. The idea that we can start from the single initial state and have multiple end states is called concurrency. We can represent this using this state diagram. Each of these bubbles is a possible state assignment of values the system can be in. We also have the entirety of the timeline, the behavior. The behavior here represents where we start, what we go through, and where we end. So 5 states, 2 behaviors. In a deterministic system, there'd be only one behavior and a sequence of states. Concurrency adds complexity. But what we often don't realize is just how much complexity concurrency adds. This is a very slightly different system. Instead of just directly modifying x, we also update it. We use a temporary variable. So there's going to be a race condition here where we can clobber data. I want you to think roughly how many different states are there in the system, both starting states, ending states, and intermediate states. Give it a thought. OK. Oh, and I think I just plugged that in, crashed everything. I apologize. I was trying to be fast. Forget that. So the answer is 13. There's 13 states in this space, and 5 total behaviors. And what we've only done is added just a couple extra lines, a couple extra points of concurrency. This is because concurrency expands combinatorically. And what I mean by that is that if you have, and I don't think this shows up, OK, so if you have n agents and m steps, assuming no interactions between them, you have, at maximum, n times n times n factorial possible states. So for approximately 2 agents with 4 steps each, that's going to be at maximum 540 unique states. Basically, for anything more than the most trivial system, the state space explodes. This represents a very simple alternating bit protocol. Each of those dots is a state. Each of those clusters of dots is about 100 states. This leads to one of the most fundamental challenges with any sort of concurrent system. The number of states grows fast. But it's not just the states. We also have to worry about the behaviors. This is because just concurrency alone does not explain a system. What if we wanted to say, for example, the system can crash, or it can return a random value, or at a higher level, it can have an error? We call this non-determinism, and we can represent this simply by saying that each agent can do one of multiple things, non-determinism. So in this case, x either increments by 1, 2, or crashes. This leads to this kind of state space. And we seem to have a problem because that slide is, OK, this leads to this kind of state space. Now note that we have only 4 states, but we have 3 possible evolutions from that. Now, this becomes an especially big problem when we combine it with concurrency. Imagine you have this as our system, and let's cap x at 6. This ends up being one of our spaces. This ends up being our state space. This ends up being a possible behavior. In fact, if you look at it, if you just cap the number of transitions at 5 steps, you have 113 different behaviors. So while the number of states expands fast, quite often the number of behaviors expands even faster. Now, this is a big problem. And the reason it's a problem is because both states and behaviors can be quote unquote bad. What we mean by bad state is that reaching it is a problem for our system, of course. Let's take this as our example. It's a trivial distributed system here, very trivial, only 20 states and 31 behaviors. You can keep that entire thing in your head, I hope. So now consider the case where this represents an autoscaling group. So it's talking about what servers go on and off for load. If we have a state where no servers are online, we have caused a critical outage. This is called a safety violation, where some property we want to hold and it fails to hold in a state. This is bad. But even if every single state is good, the behavior itself can be bad. Imagine if we have an eventually consistent database, like MongoDB. Even if every state is good, it does not lead to a critical violation. If we do not get our data to reconcile, it does not go eventually consistent, the entire behavior is a problem. We call this a liveness bug. So both individual states and entire timelines can be bad. Now, it's one thing for a system to be bad. It's another thing for a state or behavior to be both bad and present. And what I mean by that is, if we have a state that is never actually reached, if it's just so unlikely to happen that we don't care about it, what's the big deal? The response is that just never happens. Imagine that this represents something that only happens 1 in a billion times, but we hit that route 100 times a second. That's almost nothing for a distributed system. 100 times, like we build things to do 10 million events a second. Roughly how many times per year will we hit this route? Assuming it is 100 times a second, and it has a 1 in a billion chance of happening. Basically, if you load it by Halloween, it's going to go down by Christmas. It turns out that at scale, every possible thing happens. Every state is reached, every behavior occurs. This is a problem because of this little thing we call Murphy's Law. Okay, so we cannot tolerate bad states and we cannot tolerate bad behaviors, no matter what our managers say. We know better than they do. We need to get rid of these. How do we do that? People have a lot of ways. And even just skimming at a very simple level, you can find just many, many, many different code constructs. Everything from low-level hardware compare and swap to high-level supervision networks. And there's a problem with all of these. Don't get me wrong, they're all really, really valuable. I wouldn't want to work without them. But these all have a major fundamental problem in common. Can any of you see that? Pardon? Not quite, because monads, for example, are compile time. But the idea that you're talking at runtime implies code. These are all code constructs. And a code construct changes the state space. It reduces bad states and bad behaviors. But this assumes we know what we're looking for. If we do not know the state space, any intervention we do cannot guarantee we've actually fixed the problem. In this case, we've removed 15% of our states and half of our possible behaviors. 15 behaviors are gone. That means nothing if this is the bad state. It means nothing if this is the bad behavior. Without the ability to see the design, any sort of intervention is not guaranteed to matter whatsoever. We still have danger here. See, the problem here is that code is not design. Code cannot be design. It's not supposed to be design. Code represents the machine we're building. It's the implementation. It says nothing about the wider context. It says nothing about our intentions. It says nothing about the high-level interactions between our components. It just does them. If we want to fix our systems and make better systems, we need to be able to design better. We need to be able to plan better. Without that, if you don't think you need that, I've got a bridge to sell you. And there's going to be a brace condition in your code, so I can sell it to you twice. So we call this idea of planning our code, creating high-level constructs, formal specification. Specification because it describes what we want, and formal because it follows the same rules as code. We are using verified specification languages. This allows us to construct high-level ideas and work at the plan itself to find issues. And there are many tools to do this. I work with a few of different ones, but by far, one of the most effective and most widely known for dealing with concurrency and distributed non-determinism is called TLA+. This was invented by, there seems to be a bug here. Okay, this was invented by Leslie Lamport, the same guy who I talked about earlier as mattering quite a lot. He actually won the Turing Award for this. His idea is that, as mentioned, code is too low level to express our intentions. There was going to be a slide here about it, but it seems to have not worked because of, again, the Mac transfer. But just to sort of describe what I want to say here, imagine that you wanted to find the maximum of a number, right? You could use, say, iteration, go through the list, or you can use recursion, go through the list. Or you can simply say the maximum of a set of numbers is the biggest number in the set. It's the number in the set such that all the other numbers are smaller than it. We can express this using mathematical notation much more concisely than using programs. And we can also express state spaces much more concisely using mathematics versus programs. Here we're just saying that x can increase, that's it. And this represents all possible state spaces where x increases no matter what. Finally, I don't have an example here, but we can also very concisely express our invariance in this. We can say, this is exactly what our system should obey and nothing else. The reason this is important is not just because it forces us to actually talk about what we want. One of the biggest benefits about doing this is that, similar to how we can run code, we can check a specification. We can use something called a model checker to look at your design and figure out if there are any errors. And if there are errors, we can look at the trace, show exactly how to reach the error. So I'm guessing that for a lot of you, this probably isn't making a whole lot of sense. And I think part of that is because most people have not seen something like this. It's a pretty exotic field of computer science. So to sort of fix that, because I have all of your attention, I'd like to show you an example of this. And I don't want to just show you any example, because I found that when people talk about this, they usually give an example like, let's specify a clock, or let's specify a puzzle. That's interesting, but it doesn't really show how this is useful. So I want to focus on a more complicated system that might actually represent something that anybody's worked with. Who here has done something with an ETL? OK, so here's a rough description of our problem. We upload some file to some system. Let's imagine that we are uploading, say, code, or we're uploading a picture. I don't care. It's just some file that starts off the ETL process. We eventually want to produce content, whether this is a build, a set of run tests, an actual product. Again, I don't care. It's just we're going from an upload to corresponding content. We also want to be able to take down our upload, which causes the content to disappear. And finally, if we edit the upload, we want the old content to disappear and the new content to appear. Now, we need some system to do this. Let's imagine that we have a worker. We need to tell the worker that this is happening for scalability. What we mean by this then is that if we do an upload, we want to send a message to the worker. We will send the message on a perfect queue. So no duplicates, nothing out of order, no drop messages. Let's specify this system and see if we can actually guarantee any kind of interesting, useful properties from it. Now, a couple things before I start. Specs are not code. We are not writing code. We are writing a specification. There is no automatic way to translate the specification into code. Instead, we have to use engineers to do the translation. So there couldn't be an implementation error. But the guarantee is that if there are no implementation errors, our design is correct. We have created a watertight code system. Additionally, TLA Plus has a very unique syntax. So I've changed it for this slide. I'm not giving you a lecture. I'm not giving you a tutorial. I'm just demonstrating this. So I've made things look a little bit more Pythonic. But I have not changed any of the fundamental syntax or any of the fundamental semantics. If you just reverse the translation, you get a working model. OK, let's begin. Step 1, we have our imports and we have our model parameters. Step 2, we have our variables. Uploads and content will be sets. The queue will be a sequence or a list. The next ID will start at 1 and we'll increment it whenever we create new content. Next, we have some way of appending to the queue. We're going to append messages. A message will consist of the ID of the upload and the action, whether that's create, edit, or delete. Now, note that we could specify an invariant right now, that the queue only consists of valid messages. I'm not going to do that for simplicity, but that's pretty straightforward to do. Finally, we have our agents. The first agent I'm going to create is a user agent. We call these processes. This represents a single user doing whatever they want to the system. In this case, the user can create, edit, or delete. I'm going to expand those three soon, but what I want to focus on first is this either statement. Either expresses non-determinism. The user can do one of these three things. This means it'll do all of them simultaneously. If the model checker sees that either statement, it'll split the model checking into entirely new universes for each option. So it sees create, edit, delete. It creates one universe for creating, one universe for editing, one universe for deleting. Create, we just create the content. It'll be who it's from, the version. We're going to abstract away the actual details of the version. It's just a number. And the next ID. The uploads, we will add it to the upload set. We will send a message saying create it. We'll increment the ID. Simple. Delete. Then for delete, we will do the same thing, except we want a user to be able to delete any kind of content they uploaded. This adds more non-determinism. We use a with statement. If we say with some element of this set of elements, we again split into separate universes for each possible element. So two forms of non-determinism. We can either say either do this, or do this for one of these sets of objects. Edit uses both of these. For editing, we increment the version number, change the upload, send the message. That covers what the user can do. And note that actually implementing the code for the user is unnecessary. We're talking about an actual human agent here. Now, the worker is going to be similar. We first receive a message. That means we wait for the queue to be non-empty. We get the head message of the queue. We get rid of it, and then we process it. Processing depends on what we do. We can either create, edit, or delete. Now, note here that I put edit and push edit. This is because, as mentioned before, editing is non-atomic. We take down the old version, put up the new version. By using separate labels, what I'm saying here is that if we take down the old content, there is some time where another worker or another user can do something before we push the new edit. This allows us to very quickly model concurrency. Create is pretty simple. We just add it to the upload set using upload with. Then edit and delete are similar. With edit, we first take it down and store the local version we're going to use, push the new local version. Delete is similar. We just find the appropriate content to delete, we remove it from the set. That covers the entire model. We're done. Now we actually want to run it. Note I haven't given you any properties yet. I've not actually specified anything I want from this model. But it's still worthwhile to run, because by running it, I can find if it's ambiguous or not. See, TLA Plus wants us to be very explicit. There shouldn't be any cases where we can do something that isn't clear what our next step is. So if there's any ambiguities, which we'll see, it'll find that and consider that an error. Let's run it. I'm going to use the TLA IDE. This is a video of running this and actually checking the model. Pay attention to the right-hand side, assuming the video runs. Hey, it ran. Yay. OK, so you see this thing appear on the right-hand side. That's an error. We've seen an error trace. The top of that shows what the error was. The bottom shows step by step what had to happen to reach this error. In our case, something ambiguous. What this looks like is, if we actually walk through the error trace, we get the user creates an upload, then deletes it, and then the worker receives the create message. Since the upload doesn't exist, this is ambiguous. Should we crash? Should we raise an error? Should we just skip it? Should we wait? We don't know. But because we don't know, we've been ambiguous. TLA Plus says, be explicit. So I'm going to say that if the message does not exist, just skip it. If it exists, go ahead. If it doesn't exist, end. I'm going to shorten it to that for the future. We do similar things for the edit and the delete, and our model now passes. So now let's finally specify a property. This is the property I want to define, no orphan content. What this says is that for every piece of content that exists, there must exist a corresponding upload that matches it in both ID and version. Now, I want to call attention to this square diamond in the beginning. That is our specification saying eventually consistent. They can fall out of sync, but they must come back into sync. So if we delete an upload, this won't immediately fail, even though there's content that doesn't have a corresponding upload, the one we just deleted. But if we can reach a behavior where we never delete the corresponding content, we have an error. Everybody follow that? OK, I'm seeing some nodding heads, so I'm going to assume at least a couple people follow that. Hooray. Quick question, though. We have about 4 minutes on the original timeline. Can I ask for another 10 minutes? Excellent. Thank you. So if we run this, we will get an error. The error is called stuttering. What that corresponds to is us having a crash in our system. The user creates an upload. The worker receives the create. We create the content. The user deletes it. Now, after we delete, even though it's inconsistent, we have content without a matching upload. We said that it has to eventually be consistent, so this isn't yet an error. Then the worker receives the message, and then it just stops working. It's crashed. Our system has gone down, and we now have an inconsistency that remains. See, TLA Plus assumes that if you do not explicitly say, this cannot crash here, it can crash there at any point whenever. Now, often this is extremely useful to us, because if we're building a system, some parts might be more rigorous than others. We might say, this is running on very, very, very stable hardware. It will never crash. This will not be. And we can ensure properties under assuming some things crash and other things do not. In this case, let's assume that our workers are always running full-time, no downtime. I say this by calling it fair. For those of you deeper in the systems literature, this is a weak fair, not strong fair. If we do this, everything works again. So we've built a system that now works and satisfies our property. Let's scale it up. Having just one worker is not going to scale. That's going to cap at like, what, 10 messages a second? We don't want that. We want to be able to handle more than one user. We can do this by just simply saying, yeah, instead of one worker, we have 2 workers. Everything is automatically handled by this. TLA Plus will create a second process and check the entire state space with that extra worker. Now, because I'm presenting this to you as a talk, I think it's pretty clear that just by sort of meta thinking, this is probably going to fail. I think you all probably expect that. So I want to ask a different question. How many steps will it take to fail? How many things will have to go wrong in the right order for us to reach a failure? Everybody have a guess? Cool. How many of you guessed 16 steps? Because it takes 16 steps to go wrong. That's a lot of steps. In fact, it's also an incredibly complicated error trace. Very simply, the user creates an upload, the worker creates the corresponding content, the user then edits the content, the first worker edits it, pulling down the old content to push up the new content, then the user edits it the second time, pushing the version to 3. Then the second user starts to edit it, sees that the content does not exist, so it basically just skips the following to push. Then the first worker does the push, causing it to go to version 2, but the user's at version 3, so therefore we have an error. Who followed that? Who thinks you could have found this in production just by looking at your logs when things just suddenly stopped going right? Yeah. And TLA Plus is able to find it in about like 30 seconds. And not just that, but there's some obvious fixes for this. You might think, okay, we'll just change our edit logic a little bit, and this won't happen. We'll add some sort of cyclic dependency, no problem. But a lot of the fixes you might automatically add won't work. And not only will they not work, but they will have more subtle errors than what we currently have. Any change you make, TLA Plus can look at that change and tell whether or not it fixes things. Let's take one possible change. Let's check to see if we've fallen out of sync. The version we want to push is a later version than the upload we currently have. That means that our push is going to be stale. If this happens, let's cycle things. Does this fix it? No. In fact, now the error trace is 20 steps. It's an error involving the fact that now we forgot that if we delete content in the middle while we're still trying to edit it, we're going to have an edit pushed without corresponding content because the upload was deleted. We can fix this by adding a cleaner that is a batch process that just checks to see if there are any content that do not have a corresponding upload. If they don't, it'll just delete the corresponding content. This can run like nightly or whatever. If we add this, then things work. But now we've made 2 changes. Do we need the first change? Clearly the first change and the second change worked. Maybe we just need the second change. No, if you have just the second change, it still breaks. We can check that by just removing the first change. Done. This entire process takes about 5 minutes to check at most. And not just that, but we can try any other kind of variation on our problem. We can try duplicate messages. We can try drop messages. We can try adding new features. We can have partial failure. We can have everything from 10 workers, 1 of which can fail, to 10 workers, 9 of which can fail. Anything we want. Any sort of change takes about 5 minutes to add, check, and then fix. Note that these are all kinds of things that would take, well, months, weeks or months in production to actually build and see if it works. And the errors are subtle ones. These are the errors that you might not even realize are there until they've happened multiple times. But we can do this entire process in less than an hour. We can check our designs. We can look at our state space well before we've actually built the systems. I think that's really cool. But this is still an example. Does this actually work in practice? And the answer is yes. A small but growing number of companies have been using this. And when I say a growing number of companies, I don't just mean things like NASA. I'm talking about large-scale infrastructure companies like Rackspace or AWS. I'm talking about really tiny consulting shops. I'm talking about product groups. I'm talking about companies where less than 10 people in the company are engineers. It turns out that the ability to plan things out before you build them is incredible. It's truly wonderful. It lets us actually blueprint for the first time our software, think about what can go wrong, and test what can go wrong before we've started building. This is incredibly valuable stuff. And a lot of people have started raving about how useful it can be. Now, I'm not expecting you all to jump out right now and start using this full-time at your companies. No talk can do that. But at least I've hoped that I've been able to convince you that this is worth looking into, that maybe this should be tried to be investigated, see if it might be useful for us. So I'd like to finish this by quickly covering some of the ways that you can start learning how to use this. So to start, I've actually just published a book on this. So I think this is probably the best place to start with this. It's designed to take you from a complete beginner, an outsider to the space, to somebody who can use it in production. To do this, I've added a ton of concrete examples, everything from MapReduce to LeftPad to specifying business logic for a public library. It's actually out right now, and if you go to the APress site and use that coupon, you can get it for 20% off. That's like $6 USD. The next thing, if you want to go deeper, is that Leslie Lamport wrote the canonical book on this. It covers, at an intermediate level, all of the theory and the full space of what you can do with this. It's a little bit more advanced and a little bit less focused on actual model checking, but it's still a solid intermediate text if you want to go further. And then finally, you can just hire me. I do workshops. My next public workshop is in Chicago. I also do 1-day and 3-day shops on this and other tools. Send me an email, find me afterwards. I'm happy to talk more about this. And otherwise, that's really all I had to say for all of you. I know it's a little bit late. Lunch starts in about 4 minutes ago, but I'm happy to answer any questions either now or during lunch or for the rest of the conference. But in all, thank you so much for coming, and I hope you have a great day.